2022. I would like to welcome you to the second session of awards. So let me share the screen and we'll start with our awards. All right, so second session of awards. Welcome to ICSI. I hope you're enjoying the conference and all the great papers that are being presented. I want to start the awards today by recognizing the people that have earned the status of fellows in both the ACM and the IEEE. The distinction of fellow is among the top distinctions that you can get as a scientist in our communities, and both ACM and IEEE recognizes people for their contributions, their outstanding accomplishments or extraordinary accomplishments in the field of computing. So this is, in ACM is the field of computing, in IEEE is, in engineering in general, but you have to be outstanding and extraordinary to do this. And several members of our community consistently make it into those prestigious positions. So this year for ACM, in ACM, we have as fellows, and I have highlighted here all the people that have a software engineering connection, and I have bolded the ones that I have either seen in ICSI or in other software engineering publications recently. But we'll start with Paola Inverardi. And by the way, Paola was intimately involved in ICSI and in other software engineering conference, but also is a research leader, an education leader in Italy. Ranjit Jala, Nicholas Bojner, Jess Quadier, Muninder Singh, Aravinda Prasad Sisla, Scott Smolka, Tao Shi. Tao was actually a program chair recently for ICSI. Thomas Zimmerman, who's also involved in SIGSOFT quite intimately. All those were ICM fellows that were just recognized in the past year. Similarly, for IEEE, we have Brian Blake, Anita Carlton, Rance Cleveland, Yves Letron, David Law, and Robin Lutz. All these folks you'll see in the hallways of ICSI, either virtual or in person. They have been around for a while. They have made some significant accomplishments in our field, and we truly appreciate how well they represent our field in the areas of computing and engineering in general. So thank you, and big congratulations to the fellows for their accomplishments. Let's move to the ACM SIGSOFT Awards. And there was a town hall, so some of these awards you may have seen yesterday, but we really want to recognize the people that, if you didn't have a chance to attend the town hall, this is time to recognize the people that have earned awards within our society, the SIGSOFT group within ACM. We'll start with the Outstanding Researcher Award. And the Outstanding Researcher Award goes to Lionel Briand from the University of Ottawa and University of Luxembourg for contributions in software testing, software quality assurance, and context-driven software engineering research, notably in exemplary collaborations with industry. And this last piece is probably what Lionel is most proud about. If you get to talk to him, and I encourage you to do that, the collaborations with industry has been a hallmark of his work. Lionel is actually giving a plenary talk on Friday, right before or right at this time on Friday. So I encourage you to attend. As always, it's going to be fun. Congratulations to Lionel. For the ACM SIGSOFT Award for Distinguished Service, the recognition goes to Jo Atlee. Jo Atlee, she's a professor at the University of Waterloo in Canada, and she's been also a huge driver of this community as general chair, for example, of 2018, ICSI 2018, did I get that right? 2019 in Canada, for her leadership efforts. But this particular award is for her sustained outstanding service to the software engineering community and enabling a research environment in software engineering worldwide that is equitable, diverse, and inclusive. A big congratulations to Jo Atlee for her accomplishment. For the ACM SIGSOFT Awards for Influential Educator, the recognition goes to Miriam Kim. Marion is a professor at the University of California, Los Angeles in the USA. And the quote that recognizes her states that she has done outstanding achievements in undergraduate and graduate mentoring with an emphasis on research excellence in software engineering, diversity, and inclusion. Congratulations, Miriam. For the ACM 6 Awards for Early Career Researcher, the recognition goes to Xin Xia from Huawei in China. He has been recognized for contributions to AI and software engineering, mining software repositories, and empirical software engineering. Congratulations, Eugene. The award to Outstanding Doctoral Dissertation goes to Wing Lam. Wing did his PhD work at the University of Illinois under the advice of Darko Marinov and Tao Xi. And his thesis was titled Detecting, Characterizing, and Taming Flaky Test. We congratulate Wing Lam, and I believe he's now an assistant professor at George Mason. So I think he's definitely building an amazing career based on his already successful start. Now, this paper, the ACM 6th Award Impact Paper, is a retrospective paper. It's a retrospective award. This is an award that is given by ACM looking back for the last 11 years to or more to papers that have actually marked the field in certain way. And the particular paper that they have that the committee has chosen this year is a paper by Mick Kirsten and Gail Murphy, which the quote states is a paper that pioneered the concept of a task context, which has improved software practice and inspired new research. I'll highlight here that this is not Gail's first award. She has many awards for several pieces of work, and she's, again, a driver in our community. So congratulations to both, to Mick and Gail, on their Impact Paper Award. Okay, so that closes the ACM 6 Award. A big recognition to the awardees and to 6 for their effort in actually setting up of awards and setting up the committees to identify the people. A big encouragement to everyone to nominate people for these awards. We usually are a little bit slow and a little bit not proactive enough in nominating people. If you think someone deserves an award, nominate them. These committees are usually, they get a lot of really good a lot of good people, but we only get good people if you nominate them. So I encourage you to do that. So let me move to the IEEE TCSE awards. These awards, just like we have ACM 6 we have IEEE TCSE, and they are awards that we're giving in several areas that I'm going to cover right now. The first award, the Distinguished Service Award, goes to Valerie Isarni. Valerie is now a director at the National Institute for Research in Digital Science and Technology in France. It's a big research enterprise that she's running. But this particular award is for significant contributions in service, mentoring, and influence in the software engineering community. Valerie has been contributing to this community for many years in various ways, and this award recognizes that. Congratulations, Valerie. The Education Award, the Distinguished Education Award from TCSE, goes to Didar Sowi. So the quote says, for outstanding contributions to software engineering education by her long-term efforts to increase diversity in the student body studying computer programming. So big congratulations to Didar. She is at the CISRO Data 61 in Australia, and we appreciate her efforts and congratulate her on this award. This is yet another special award from IEEE to recognize people that have done just so much for our community that they earn this Lifetime Achievement Award. And this year, the award goes to Michael Jackson from Open University in the UK. Um, he has done just so much for the community, so many seminal pieces of research. And the quote actually recognizes that by saying, for more than 5 decades of contribution to academic and industrial software engineering and its research, influencing generations of software engineers. So if you haven't read some of the, I know 5 decades sounds like a long time, uh, but you should look at the papers from Michael that for example, the requirements papers, some of the seminal papers that I read in graduate school are still fresh when you read them today, and I encourage you to look at them. Congratulations to Michael. We're just really, really lucky to have people like that in the community. This is another really special award, the Distinguished Women in Science and Engineering Leadership Award. This year, the recognition goes to Margaret Burnett. Peggy is a professor at Oregon State University in the U.S. She has contributed, enormously to the software engineering community, to the Kite community, to develop, tons of young talent in our community. She has also, her research accomplishments are also amazing, but setting a new field in user software engineering. But this award is actually for her leadership as a ceiling breaker. She, for decades of work, breaking glass ceiling for women in computing and software engineering. Very, very lucky to have Margaret in our community, and big congratulations to her on this award. IEEE also recognizes Rising Star Awards. This year, they were just two candidates that they couldn't decide upon. They were just so good, both of them, that they recognized both candidates. I'm not sure. We'll have to see whether that means that they share half of the award or they earn one award each. I believe each of you will get a plaque on this. But the candidates, the award winners are by Shaki Ray and Sonia Haiduk. And if you get a chance to chat with them, you'll see why they're getting these awards. Uh, they are they're just extremely bright and fun to talk to, these researchers, and they're both recognized for being innovative in a slight, within software engineering, but different areas. Shaki is working on software engineering and AI that has impacted our community, that is having impact in industry. Sonia has been working a lot of software maintenance and evolution, and we're just really, really in good hands for the next generations with this type of rising stars in the field. Big congratulations to Baishaki and Sonia on this award. The TCSC Award for New Directions Award goes to Christian Kadar. Christian is a professor in Imperial College in London, in the UK, and Abhik Rochaudhuri is a professor at the National University of Singapore in Singapore. Both of them have made similar contributions to symbolic execution, and this particular award is for symbolic execution for test generation and program repair, where I believe Christian is on the test generation side, and Abhik is more on the program repair side. But both of them really well recognized in the field of test generation, program analysis, and setting up these new powerful directions for the field. So congratulations to both Christian and Abhik, both actually also leaders, emerging leaders in our community, running conferences and doing other things. But this particular award is for the research in establishing this new research direction. Congratulations to both. And this is a time where this is actually a different award. This is not part of the standard TCSC award, but our general chair, Matt Dwyer, is also the recipient to the Harlan Mills Award. And before I say this quote, I'm going to show you, for the ones that are online, you're going to witness the magic of mid-space in this moment. This is a feature that is just being released. So hold on, I'll show you what it does. So congratulations to Matt. There you go. For contributions to the specification and analysis of software.
Thank you.
All right, everyone. Take care. This concludes the award session, and we're moving on with our keynote. Bye-bye.
Okay, when he gets back over there, an unscreen share, we'll get started. Oh yes, applause for everyone. Congratulations to everyone. Wonderful work. Really looking forward to the future of this field. A lot of great leaders coming up through the ranks. So what I would like to do now is introduce today's keynote speaker. Professor Phil Koopman is a faculty member in the ECE department at Carnegie Mellon University. He spent about a decade in industry working on hardware and embedded computing systems before joining CMU, including being the chief architect of a novel stack-based microprocessor. I personally first heard about Phil's work when I got a copy of his book, Better Embedded System Software. And even if you're not an embedded systems person, I highly recommend this book as a sort of a holistic approach to domain-specific software engineering, focused on embedded systems, of course, but any domain-specific software engineer could learn a lot from this book. While he was at CMU, he collaborated quite a bit with the National Robotics Engineering Center. And this helped establish him as an expert in stress testing of autonomous vehicles. In addition to his scholarly work in the area, Phil has also worked to kind of explore and inform practical solutions that could be adopted more broadly by industry. So for example, he co-founded a startup that focuses on testing autonomous vehicles. And he's also served as principal author of the ANSI UL 4600 standard for safety for the evaluation of autonomous products. This is a US standard that was released in 2020. If you've not heard of ANSI, that's the American National Standards Institute, and UL is Underwriter Laboratories. It's an organization that's been around for over 100 years in the US, and it establishes safety certification standards for a wide range of products. So I think if you look at the bottom of your toaster, for example, you'll see some kind of UL approval there. Well, the first standard to govern safety, assurance of autonomous systems is the one that Phil was the principal author of. And it describes safety requirements for the higher levels of what's called the SAE autonomy scale, 4 and 5, up where the human is not in the loop. The human's not even there as a safety backup. And I think that we all know or have the suspicion that autonomous vehicles are going to be operating on our roadways sometime in the future. It's just a matter of time. And in my personal opinion, it's people like Phil who are going to help set the guardrails so that when that time comes, these systems are going to be able to operate, as safe as can be reasonably expected. Let's put it that way. So Phil is here live, and he's looking forward to answering questions and to the discussion. But he's prepared his talk as a recording, and I'm going to play that recording out now, and it lasts about 40-something minutes. And then we'll have plenty of time for discussion. So I'll do that now. Except I don't see the recording. This is where Ed helps me. So Ed, when I change live stream source, I see live backstage and filler video, and that's all I see.
Yeah, hey Matt. I'm just going to put the filler video on for a minute and
This is Phil Koopman, and I'll be talking about autonomous vehicles and software safety engineering. As an overview for the talk, I'll start by talking about how autonomous vehicles are almost solved, but the almost part is very misleading. They're actually quite a long way from cars being able to drive city to city with no one paying attention. There's a huge challenge here, and the huge challenge is safety. Autonomous vehicles present additional challenges beyond what we see in conventional vehicle safety. And I think that perception edge cases, the ability to decide what something is and to predict what happens next, is a really limiting factor in the safety of this technology. Beyond that, testing alone is not going to get us to safety. We need more than testing, and I'll talk about why that is and the types of approaches that can be taken. Generally, safety requires a standards plus safety case approach, much more than just laborious brute force road testing. You need a life cycle argument to support deployment safety. And I'll talk briefly about a standard, ANSI UL 4600, which is heavily concentrated on, did you think of that? Thinking about all the things that can go wrong to make sure that they've been accounted for in understanding the safety of an autonomous vehicle. The autonomous vehicle problem has been 98% solved for more than 25 years. This may come as something of a surprise, but back in July 1995, a Carnegie Mellon minivan went from Washington, D.C. to San Diego 98.2% hands off the wheel in an exercise called No Hands Across America. It was the CMU NavLab 5 vehicle, and it did that on interstate highways across the country with 98% driving itself down the highway. Moreover, in 1997, there was the Automated Highway System event where there was a demo on an interstate highway near San Diego where not only did a minivan go down the road, but also a platoon of coordinated vehicles and even a city bus. And again, they weren't perfect, but they were very, very good. So this technology has been around for a long time and almost there, but not quite there. That last 2% is taking a long time. So the issue with that, first of all, to deploy this technology at scale is, what about that 2%? Why is that so hard? At Carnegie Mellon University, there's the National Robotics Engineering Center, and this place has had 35 and more years of cool robots. You can see a timeline in the picture. One misconception about autonomous vehicles is they started with the DARPA Grand Challenge. Well, from this timeline, that's kind of at the midpoint. These things have been around a long time. From a safety point of view, in the early days, there was the big red button machinery safety approach. If something went wrong, somebody slapped the big red button and the whole thing shut down. Over time, that became less and less viable as the systems became more complex and the operating conditions became more difficult to control with just a stop button. Think about it. If you're at 100 kilometers per hour on a highway and the big red button locks up all the wheels and brings the vehicle to a stop, that's going to be a pretty messy exercise. So you need to be more sophisticated when things look less like a piece of machinery in a factory and more like a vehicle going at high speeds down roads. Well, how do you do that? Well, you need to transition from machinery safety to software safety. I was fortunate enough to be at the center of a lot of this as the principal investigator for 10 years worth of research on this topic at NREC. There was an excellent team at NREC who did all the work. I was the principal investigator. But this talk builds on the insights from that team and a number of other experiences I've had. Let's start with some basics. What's software safety engineering? Well, safety is a system property. It's beyond just correct code. Yes, it's really nice to have correct code. If you have bugs in your code, it's going to be difficult to get safety for sure. But just having perfectly written code that exactly meets the requirements does not necessarily get you to safety. That means, of necessity, safety engineering is more than just looking at requirements and implementing code. Part of it is writing the requirements, but even more is understanding that safety affects the requirements. The heart and soul of most safety engineering has to do with hazard mitigation. The idea is you identify the hazards, things that can go wrong. If X goes wrong, that could result in a loss event, and we need to understand how that could go wrong and what the loss event is and things like this. Those things that can go wrong include hardware failures, tool defects, environmental surprises. These are systems that are operating in the real world. And so assumptions that, for example, you will never have a computational defect due to a radiation-induced upset, that's not the real world. Those things happen in the real world. So you have to account for those, especially if you're deploying at large scale where lives are on the line. Once you have a list of hazards, for each hazard, you predict the risk. And typically the risk is probability times consequence. The idea is that if you have something that can be really bad and it happens all the time, you need to do something about that. If you have something that has a very, very low consequence and it almost never happens, maybe you can just live with the risk. The things in between are more typical, and that's where you see the hazards being converted over to risks, and then you do risk mitigation. The tricky part for all of safety engineering is probably never times near infinite consequence. What's 0 times infinity? Well, there's a lot of economic pressure to say, well, we're not going to worry about it because it'll never happen. But usually when people estimate the probability, they're a little bit optimistic, and things tend to happen that people thought wouldn't happen. So what you really need to do in safety is weight it a little bit more towards the outcome, that even if you think it'll probably never happen, if it's a really, really bad outcome, you still have to find a way to mitigate the risk. If you think about nuclear power plant safety and aircraft safety, you'll find that they spend a lot of effort on things with very low probability, but catastrophic outcomes, and even then, sometimes they get surprised. Once you've figured out all the risks, then you have to mitigate them. For each hazard, you say, here's the risk, and the higher the risk, the more work I put in to make sure it's mitigated down to a place where the entire system has a reasonable remaining acceptable risk. The mitigation typically involves engineering rigor, such as process quality, doing some analysis on the system, some testing, some redundancy patterns, and so on. It also involves the use of functional safety. Functional safety is there may be an internal defect for your system, so you take approaches to mitigate those defects that are eventually going to happen. For example, if you have a malfunctioning component, you detect that it's malfunctioning and you shut it down to get yourself to a safe state, potentially with some sort of backup system taking over if it seems necessary. There's also safety of the intended function, SOTIF. The idea there is that your requirements in the real world will never be complete. There'll always be things that you missed if you're operating in the real world. That means you need resilience to requirements gaps. You have to deal with inconsistent sensor data. You have to be able to at least remain safe even if you can't operate in unexpected environments. The big idea here is safety engineering is not simply going from requirements to perfect code. Safety engineering explicitly deals with understanding the hazards in your system and mitigating risks, because no system is ever perfect, but a safe system still has to deal with the fact that that's the case. Autonomous vehicle safety is even more complicated than conventional system safety. All the things on the previous slide should be done for any conventional computer-based system when safety matters. But for autonomous vehicles, we need to do more. There are public expectations. People expect superhuman machine performance, including safety, even if it's a difficult, ill-structured task. People are allowed to make mistakes, but computers aren't supposed to. Now, anyone who's worked with computers know that computers aren't perfect, but the default expectation is if something goes wrong with the computer, we need someone to blame because computers aren't supposed to have problems. The other issue is that people are too easy to give trust. They may sit in a robotaxi and everything looks fine and safe and boring for 5 or 10 miles, and they decide it's safe. And then you get a big backlash if something happens on mile 11. Well, those numbers are far too low to establish trust in a system, but this is how people behave. So there's always the risk that if a system is generally well behaved for a short period of time, people overtrust it and feel like the trust has been breached when something bad happens later. Beyond that, there are substantial technical challenges. Machine learning safety is still a work in progress. All the hype you hear and all the autonomous vehicle companies pushing to put things on the road might make you think that it's just around the corner, maybe this year, maybe next. But in fact, understanding safety for machine learning is very much a work in progress. And no matter what you hear, it will probably take longer than what people said for this to be an at-scale safe technology. There's another technical challenge, which is that you're trying to use an inherently statistical approach to deal with high-severity rare events. The issue is statistical approaches struggle to make claims of things involving 99.8 more nines after the decimal type of events, which is what you end up with life-critical safety. Possibly the biggest issue is the historical industry culture clash operating across multiple different types of stakeholders who have to work together to get autonomous vehicles on the road. One is the autonomy researchers. They've spent decades doing amazing, cool, small-scale demos. I showed a picture from just one research group showing all the cool things they did. And for them, historically, it's been about the cool, small-scale demo. Now, all of a sudden, they're betting huge sums of money on making something real and deploying it at scale, which is a different challenge than they've traditionally faced. Then you have Silicon Valley, the people putting all the money in. They're used to moving fast and breaking things. Well, moving fast, okay, that sounds nice, but breaking things is not so good when there's people in vehicles involved. So that's an issue. That approach will have to be moderated because of safety. Then there's the automotive culture. The automotive culture understands safety, but is still very aggressive on cost cutting. And one of the strategies they've hit upon over the years is putting the driver in charge of cleaning up any small safety messes and saying the driver's supposed to mitigate anything bad that happens if it's at all possible. And so they've taken to blaming the driver for mitigating things that are otherwise equipment failures. Finally, you have the regulators. The regulations today are very test-centric. Take a car out on the road. If it seems to behave okay, then it must be safe. And that no longer works in the era of software, but the regulators haven't changed. They generally have weak digital safety expertise that is changing slowly, but the regulatory world still behaves as if cars were mostly mechanical and electrical components and has comparatively little experience at dealing with computer-based system safety issues and in particular with software. The core issue here is, should you trust an autonomous vehicle? Now, to its credit, the industry has figured out that this is actually what matters. One of the companies put out a voluntary safety self-assessment report, and their headline figure is, it's a matter of trust. They're absolutely right. The question is, should we trust autonomous vehicles to be safe? There are a number of issues here. In particular, regulatory issues are very difficult. Stakeholder expectations are difficult, and so on. But the one I'll be talking about here is the heaviest technical lift, being perception and prediction safety. That's the hard thing, and we're still working on it. Let's dive in a little bit to what I mean by perception, and prediction ends up being part of this. Perception builds the world model. You have a vehicle operating out in the real world. Things happen in the real world. There's a kid kicking a ball, maybe chasing a ball. And there are sensors on these vehicles. There's video, there's LiDAR, there's radar. And all those sensors get combined by a perception system to build a model of the external world. Hey, I think there's a child chasing a ball into the street 10 meters ahead. So that's the perception system. Note that it's both perception in terms of what objects there are, but also implicitly prediction what will be happening next. The child is chasing the ball, so we expect the child will keep going after the ball. Wherever the ball is, the kid will end up. Once there's a world model, you can do path planning, you can do motion control. And to be sure, those are complicated, difficult challenges. But they pale in comparison with the challenge of assuring that the perception is done in a way that is suitable for life-critical systems. The perception typically relies very heavily on machine learning. And the question is, how do we actually assure the safety of these systems? How do we make sure that the vehicle is going to know that this child is about to run into the road and avoid hitting the child, which involves not only detecting the child, but also realizing the child is likely to move in a certain direction and then commanding the vehicle to make sure its path does not intersect with the child. If we can do that with extremely high confidence, we might have a basis for trust in the vehicle. But how do we get there with machine learning? It turns out that for perception, the edge cases are likely to be the limiting factor. Sure, it's easy enough to detect a child with relatively high confidence, 90% plus. But for life-critical systems, you need much, much, much higher confidence than that. You basically need to always see the kid in the road. Machine learning is amazing at what it does. In general, it works by being shown a bunch of examples, learning statistical patterns in the examples, and being able to recognize when it sees things that are similar in the future. So if it's seen a bunch of kids with a certain type of clothing in a certain background running into the road, it'll probably be able to recognize that, as long as it looks like things it's already seen. But the world is full of novelty. And so one of the issues with these systems is something can be different, perhaps subtly different. Perhaps, and we've seen this in the real world, it can be as subtle as changing color of clothing changes the perception performance. So you have this world full of novelty, and the machine learning hasn't been trained on every possible thing and may have big gaps in the training that turn out to matter in the real world. Along with this risk of missing pieces of relevant training data is the issue that perception and prediction based on machine learning tends to be poor at recognizing when it's just guessing. We've seen failure modes in which it will have extremely high confidence and it's completely wrong, typically because it's seen something it hasn't trained on. Now, I'm aware that there's lots of research in this area, and that will eventually make progress. But I'm pointing out that the problem is inherently very difficult and therefore a challenge to apply it to real-world systems. Just to bring home the type of problem we're talking about, let me run a little exercise here. I'm going to ask everyone who's watching this to look at a picture and decide if it's a person or a chicken. I'm making the problem pretty easy. You're becoming a human binary classifier. I'm telling you the correct answer is either person or chicken, so you don't have to worry about anything else. I'm going to show you a picture at the count of 3, and when you see the picture, I want you, preferably out loud if you can, to say the first word that comes into your mind. Do you think this is a person or a chicken? Get ready. 1, 2, 3. When people see this picture for the first time, they often have an experience chicken, no wait, person, because there's a lot of chickenness in this picture. It's mostly chicken, but once you look a little bit closer, you'll see a woman's face peeking out, and then you realize, oh no, it's not a chicken after all. It's a person who happens to be wearing a chicken suit. The difference between chicken and person has large implications both in terms of predictive behavior and the importance of not hitting a person if there's any possible way to avoid it. I ran this picture through a classifier online, and it was supremely confident there was no person, 99%. It thought it was a chicken. It didn't really see the face. There are 2 issues here. The first is if you haven't been trained on people in chicken suits, you're likely to get this wrong. But the second, more disturbing thing is the system was incredibly confident that it was not a person, even though it was completely wrong in a way that any human could tell. That's the issue here, that if you see a rare event that looks like something the machine learning has learned, but is completely different in terms of what matters in driving, you might have a system that does completely the wrong thing while not even realizing it's making a mistake. I'm going to call these edge cases. The definition I'll use for edge case is things you didn't train on, you didn't think of, things you didn't see in testing. In other words, things that come as a surprise to your system. It's the stuff you didn't think of. And the limiting factor for a lot of autonomous vehicle safety is simply what do you do about the edge cases? What do you do about things you haven't seen before? And how do you make sure, well, maybe you can't work 100%, but how do you make sure you at least know that you're in a situation you weren't designed for so you can do something reasonably safe? The challenge for perception and prediction is covering everything. And there's a lot of everything in the real world. That's the issue. How do you cover all the possible unknowns? Well, here's someone who decided it'd be fun to make a retired jet fighter into a car. I guess apparently it's a car. May not look like one, but anyone driving down the road, a human driver, I think would eventually figure out, okay, well, I'm going to treat that thing like a car. Now you may say, well, I've never seen an airplane on a road. It's like, well, I have, because at some military bases, you go down a road and there's a stop sign and you're not stopping for other cars. You're stopping for the fighter jets going from the hangars onto the main runway. And I can assure you that your car insurance does not cover the collision damage to a modern jet fighter. So this actually happens in the real world, but it may not be something that the system has been trained on. Then there's issues such as puddle of water. How deep's the puddle? Well, this one turned out to be pretty deep. And so you have to decide, well, yeah, it looks like a flat road, but that looks like puddle, and I have to be a little bit careful. Now, to be sure, this is a human driver who made a mistake and went into the puddle. The machine learning-based systems aren't going to be perfect. I get that. But these are the kind of things you have to think about, look at the risks, and decide how much of these things you can cover, and decide which things you're willing to take the chance on. There are unusual road configurations. There's the roundabout of roundabout. There's only the one, from my understanding. But if that's the town you're driving in, you have to be able to deal with it. So if you train a system that's never seen this before, expect to have a lot of surprises when you start operating in this one town. And yes, in fact, on real roads, there are people running around in chicken suits. Usually they have a fried chicken advertising sign in their hand, but that's a thing, and you may not see it, but when it happens, you have to do the right thing. Finally, there are also things that are quite subtle. For example, here's a person and a bicycle. Now, is the person pushing the bicycle? I'm going to say yes because their hands intersecting the handlebar. Is the person riding the bicycle? I'm going to say no because both legs are straight and feet are flat on the ground and there's no separation. So probably this is a person walking next to a bicycle. Why is that relevant? Well, the expected speed of a person walking next to a bicycle is different than a person riding a bicycle. And this is not a hypothetical difference. This confusion between person and bicycle was one of the contributing causes to a fatal crash involving an autonomous vehicle test platform. So these kind of things matter in the real world. Well, how are we going to figure out what all the edge cases are? When the industry started, they said they were going to public road test, and if they did enough testing, they would see all the problems and they would fix them and they'd be good to deploy. We're years and years and years later, and eventually the companies figured out that that wasn't enough. It's good for identifying the easy cases. Getting that first 90%, yeah, it's pretty straightforward because stuff you see every day, well, you're going to see it every day, you can train on it, you can fix it. But the rare cases, the events, are an issue, and more importantly, it's both expensive and potentially dangerous. Uber ATG found this out the hard way in Tempe, Arizona. There's a photo from the crash investigation in which they struck and killed a pedestrian. Even though there were technical issues that contributed to the crash, in the final analysis, the problem was not technical. The problem was an inadequate safety culture. And that's when safety really became on the minds of a lot of the big players in the industry. To this day, there's still a wide variation across the different companies and how much they've learned from that crash. The road testing continues, and we're seeing an increasing number of mishaps out on the roads. There was the Uber fatality that I mentioned in March 2018, and also worth mentioning is that for that and other reasons, the facility closed down in January 2021. Local Motors had a crash in Canada in December 2021, and the company closed shortly thereafter. Pony AI had a crash in California in October 2021. Fortunately, there was no one in the vehicle and no other road users were hurt, but they had their uncrewed test permit revoked, and I have to imagine that set them back. WeRide was filmed having a sleeping test driver also in California roads in October 2021, but the company just deflected the issue as no big deal, and there was no apparent regulatory action. EasyMile has had phantom braking injuries to passengers who get thrown around in the interior, both in 2019 and 2020. Now the thing is, there's a standard for doing crewed road testing, SAE J3018, that's been around since 2015 and was updated as recently as 2020 in light of the Uber fatalities. But there's only one company using this standard. So we have a Society of Automotive Engineers standard for how to do safe road testing in terms of making sure the safety driver is alert and qualified. And there's only one company who says they follow the standard. This doesn't seem right, but that's the world we live in right now. Despite the dangers, we see the autonomous vehicle companies, for the most part, spending huge amounts of resources on road testing. Now let's ask, how much road testing do you really need to prove safety? Well, if there's 100 million miles between fatal crash, which is the case in the US, including all the drunk drivers, by the way, you need to test between 3 and 10 times longer to get statistical significance. That's 1 billion miles of testing. Well, how far is 1 billion miles? That's 25 round trips on every paved road in the world, and you're only allowed to have fewer than 10 fatal crashes in that 1 billion miles. And by the way, if you make a change to the system, in principle, any change, but in practice, any big change, whatever big means, that's another problem, you get to start over. So there's no way that brute force testing is ever going to show that this technology is safe. It's too expensive, it takes too long, it's just not feasible. To be sure, you want to do some road testing, but you have to do something else on top of it. Well, people said we can do closed course testing. It has two advantages. One is it's safer because you can control access to the road. You're not sharing the road with other public road users. And also you can set up whichever scenario you want. If it's unlikely in the real world, you can do it on purpose on a closed course. But it's expensive to run out these test courses. There aren't many of them. And it's hard to get a lot of miles, so it's not scalable. But another more subtle problem is you only test things you think of. Volvo famously does a moose test to try and avoid hitting moose and making sure that if you hit a moose, the vehicle's still going to be safe anyway. But they very famously failed when they went to Australia and they hadn't programmed in kangaroos, and their distance estimation software had an issue when the kangaroo's feet left the ground. So they'd assumed that there would always be at least a foot on the ground. So if you haven't thought of it, you're going to miss it in closed course testing, no matter how hard you try. Because of the expense of closed course testing and public road testing, people turn to simulation. Simulation is highly scalable. It's certainly less expensive than road testing, but it has two problems. The first one is you have to validate the simulation. You have to do tool qualification. How do you know there's no defect in the simulator that's giving you the wrong answer that will cause your real vehicle to have a problem out of the real world? And the other one, it still only tests things you have thought of. So the issues here are, even if you go heavy in simulation, you have to make sure your simulations are suitable for life-critical application, and you have to make sure that you've modeled all the real-world events in the simulation, and we're back to all the infinite number of weird things that can happen in the real world. That's still a challenge. To put this into perspective, let's say you're going to make an argument, oh, my autonomous vehicle is safe because I use some simulation, some other things. How does that shake out? Well, to trust the system, you would have to put your own child, notionally, in front of this self-driving car. It has 10 billion simulation miles, but what if there's a simulation error? It has 100 million miles of data collected to try and sweep up all the edge cases. But what if it's still missing some of the edge cases that happen less frequently than that, but when they happen, they happen? Maybe there's 10 million miles of road testing. Now, 10 million miles is not a billion miles by any stretch, but it might be okay if it's there to make sure that the data you've collected matches the real world and to validate the simulation. But what if there are high-risk simulations that you didn't try in road testing, and that's where the simulation differs from the real world? So you have to take care of that issue. And what if the entire thing was designed with research quality tooling that didn't have any safety qualification for the tools, for the compilers, for the simulators, for the machine learning training and management software, and so on? And what if there's a 5% error rate in the labels for your training data? That's not an unusual kind of number. Are you going to trust that system? Well, the issue is you can't just say the car needs to be safe. Not only the software stack, but the entire tool chain and data quality needs to be validated to be suitable for life-critical systems. This is a heavy lift, but it's the kind of thing you need to do if you're going to build a life-critical system. The way industry handles safety issues is they rely on standards. In every industry except cars, there are a set of safety standards that have been published and the industry follows. Either the regulators make them follow it or the customers make them follow it. So if you get on an airplane or you get on a train or you rely on a power infrastructure or you have a petrochemical plant somewhere nearby, in all those cases, the reason you generally trust them and believe that they'll be safe is because there are industry safety standards they follow. The car industry is dramatically different. The car industry is not required to follow their own safety standards, and in many cases they do not. Nonetheless, the standards are there. So let's go down the automotive standards. There's ISO 26262 functional safety. That covers runtime faults and design defects. This standard has been around for more than a decade, and it covers software and computer-based system safety for conventional vehicles, but is still applicable to autonomous vehicles. It assumes, however, that you know all the requirements. You have to have a complete set of requirements for this standard to really do its job. That works for things like brakes and electronic throttle control, but it's not as much as you need for something based on machine learning. For that, there's another standard, ISO 21448, SOTF, Safety of the Intended Function. And the idea here is it helps you identify and mitigate unknowns. The standard explains how you search for unknown unknowns, and when you find them, you pull them into the requirements, and you mitigate the risk, and you continue until you run out of unknowns. That standard is great as far as it goes. It gives you methodology, but it still helps to prime the pump with a list of unknowns so that you don't have to discover every single one for yourself the hard way by driving hundreds of millions of miles. You need, did you think of that lists? Here's an example in downtown Pittsburgh. A bus was driving along and all of a sudden the ground opened up and swallowed up the back end of the bus. Fortunately, there was a human driver who had the presence of mind to say, gee, this isn't right. I think I should let my passengers out before something worse happens. and eventually a giant crane came and pulled it out of the hole. But these types of things happen. There's an essentially infinite list of things that can happen. You will not have seen all of them during your testing and training. On the other hand, if you had a list that said, think about sinkholes, you don't need to wait for the sinkhole to happen to think about it. So to get safety, you need more than just applying these two standards. You need a technically substantive safety argument. I'll get to what that means in a moment. You need evidence of coverage initially at the time you deploy and feedback from surprises. You want to have thought of most of the surprises you can, even if they haven't happened to you yet, and make sure you have them covered. You need to then realize and have the humility to know that you will never think of all the surprises. So you need a very strong continuous improvement process to notice when things go wrong in the real world, even if it does not involve a crash, and learn from them so you can prevent bad things based on initial symptoms instead of waiting for the bad outcome to fix a problem. And you need a way to organize everything so that all these pieces come together to ensure safety. The way to organize them is called a safety case. A safety case helps you organize the argument that you think your system is safe. Generically, a safety case starts with a claim, which is a property of the system, such as the system avoids pedestrians. Then there's an argument as to why this might be true. For example, our autonomous vehicle detects and maneuvers to avoid pedestrians. Then there's some evidence to support the argument. There might be tests, analysis, simulations, and so on. Generally, a safety case will be pretty complex, so there'll be a number of arguments and sub-arguments. For example, there might be an argument that we detect and maneuver to avoid pedestrians. Well, the sub-arguments are we detect pedestrians, and here's some evidence to show you why that's true. And we maneuver around detected pedestrians. Here's some evidence to show you why that is true. And we stop if we can't maneuver. Here's some evidence to show you why that's true. To be sure, these can be somewhat complex. But the nice thing about having this kind of structure is you can organize all the material. You can look at small pieces, and you can build up arguments on top of other arguments to try and support your claim. Beyond just saying that the vehicle will be safe when it drives down the road, there's more to the safety argument. There has to be maintenance-related safety. What maintenance is required? Has the maintenance been done? How do you know the maintenance was done effectively? There are safety-related aspects of the life cycle. For example, have you managed your requirements properly? Have you done the design properly? Is your machine learning training system effective? What about the handoff to manufacturing? What about putting cars into deployment? What about the supply chain? What about field modifications and updates? Operation, retirement, disposal. The idea is that a lot of things happen during the life of a safety critical system, and all of them have to be done properly to maintain safety. In line with this, the safety case is not just something you do at design time, but rather each vehicle has associated with it a specific version of a safety case that is kept updated during its entire life cycle. Creating a safety case of this complexity and scope sounds like a complicated undertaking, and it is. To help support the industry with that, there's the ANSI UL 4600 standard for autonomous vehicles. The standard tells you how to evaluate a safety case, which means that it doesn't tell you how to build the safety case. It doesn't tell you how to build the vehicle. What it does is provide almost 300 pages of criteria that can be used to assess whether the safety case for an autonomous vehicle has everything it needs to ensure safety. It provides for independently assessing the safety case, allows mix and match supporting standards. So the ISO 26262 and the ISO 21448 safety standards I mentioned previously, in fact, are quite compatible with this and would provide substantive parts of the arguments for the ultimate claim that your system is acceptably safe. It discourages questionable practices. Safety engineering has learned a lot of bad things that you should avoid doing in the past decades, and a large number of them are included in the standard as cautions or pitfalls to embody lessons learned. It has extensive did you think of that lists, things that you should remember to think about, such as, for example, sinkholes, but a lot of other things, to make sure your safety case is not missing things that are fairly well known, but you just didn't happen to see in testing or just didn't happen to occur to you during the system design. Importantly, it treats unknowns as first-class citizens. These systems will deploy with incomplete requirements, with gaps in the training data. There's just no way around that. Even if you got it perfect on the first day, the world would change the next day, and now you'd have a gap in your capability. So unknowns are treated as first-class citizens with a balance between analysis and field experience. In particular, there is a requirement to use field monitoring to feed back safety case improvement so that you report data from the field so that you can notice its weaknesses and you can fix the problems by updating the safety case and mitigating emergent hazards with a high probability of having the fix out before you actually have a loss event. The findings from assessments and field data are not only used to improve the system, but also to update the practices incorporated into the standard. The second edition of ANSI UL 4600 was issued in March 2022. The third edition is already underway and will address the special needs of heavy commercial trucks in addition to light vehicles, which are already covered. Wrapping up, we're still on the path to achieving autonomous vehicle safety. There are a number of challenges still remaining. The first is that there needs to be a cultural reconciliation within the industry. We need to get safety for on-road testing right. The driver and the vehicle need to work together to make sure that there are no more crashes that make the news and degrade trust in the industry even further. The good news is SAE standard J3018 exists and would help. The bad news is that most of the companies in the industry not only aren't pledging to follow it, but are actually fighting against regulations that would require that they follow it. The industry in general needs to mature beyond a rush demo mentality. I understand the pressing need to raise the next round of funding, but if getting the next funding demo to work involves cutting corners on safety, eventually that's going to come back to bite not only that company, but the entire industry with a loss of trust. We need to have stakeholder trust for acceptable safety. The technical problems need to be resolved. There needs to be system-level safety for machine learning, and that's still a work in progress. But we also need to normalize the practice of independent safety assessments. What we found in every other safety-critical industry is that if there is no independent assessment of safety, you don't get safety. And right now, the industry is fighting very hard against independent assessments, especially from external agencies, and that's going to need to change for us to really get safety. The industry needs to embrace safety standards. Right now, they're the only safety-critical industry that doesn't really want to follow their own standards, and that's going to have to change. We need to reform the standards optional regulatory approach taken now. Now, the industry can do that on its own, or they can have the regulators come in later after big crash. It's up to them, but that change is going to have to happen to actually get safety at scale. We need to do traditional software safety, plus critically, we need to be able to account for unknown unknowns at deployment, which is a new thing for any safety-critical industry. The good news is that the ANSI UL 4600 standard specifically addresses the unknown problem by using field feedback to help improve both the system and the process. I was asked to briefly introduce some discussion starters for the Birds of a Feather session associated with this topic. The Birds of a Feather session will be called Autonomous Vehicles and Software Safety Engineering, and here's some starter questions and topics and thoughts to think about so you can come prepared to contribute. One is, should software developers share blame for fatalities? Right now, the autonomous vehicle industry is going state to state campaigning for regulations that make the operator responsible for anything bad that happens on the roads. It's unclear who the operator might be for an uncrewed vehicle, but it's probably not the manufacturers in most cases. Is that the right thing? Should the software developers actually have some blame if there's a fatality or other mishap? Interesting question. Associated with that are the ethics of who gets to decide when it's okay to deploy beta software on public roads, and should that even be a thing? Now, I said the word ethics, so I want to set a ground rule for the discussion. We're not going to be talking about the trolley problem because it's irrelevant for practical autonomous vehicles. There's a YouTube video here. If you really want to understand why I said that, watch the YouTube video. But the word trolley associated with the word problem is strictly off limits for the birds of feather discussion. For machine learning, how do we ensure training data coverage of the operational domain? How do we make sure the training data covers everything you're going to see, keeping in mind that rare events are going to be a challenge? How do we account for high risk of heavy tail events? I'm doing a keynote at the SEAMS conference, which is affiliated with ICSI, and you can see my SEAMS keynote talk for a lot more detail what I mean about that. But this is a major challenge. What about using commercial or research quality software for life-critical systems? Is it okay for software that was part of a PhD thesis or was downloaded from GitHub to be used in a life-critical system? How much more review do you need to do? How do you assure that that software is suitable for life-critical use? Don't forget, that includes simulator software, simulation object models, machine learning development tool chains, pre-trained models, DevOps, cloud infrastructure, SaaS tool chains. Think about it. If there's any piece of software that could cause the autonomous vehicle to not behave in a safe way, whether directly or indirectly, at some point that becomes life-critical software. So what's the plan for dealing with all that stuff? And more generally, what are the gaps between ICSI research results and AV system level safety? There are surely some gaps, but it will be interesting to hear people's perspective on what those might be and how we might address them. Thanks for attending my talk, and I look forward to.
All right. Well, hopefully you enjoyed that talk as much as we did. We're going to open up for questions now. So please type your questions in the chat, and we have one. We have one from Reed, so I'll just read it out. So in the U.S., we have a long history of engineering our cities for cars rather than people. And there's a push to reverse this trend by building more infrastructure for pedestrian, cycling, public transit, traffic calming, etc. At the same time, this creates perhaps a more complex environment for autonomous vehicles to navigate in. How do you think this affects the safety calculus for self-driving vehicles? When we're shifting from the traditional road-based environment now to one that admits more diverse forms of traffic?
Interesting question. Some people say, well, autonomy is the solution to all our urban mobility problems. And I've never really bought into that one. If you make the price of a taxi cheaper, it's not going to make demand go down. So that's something to keep in mind. In terms of all the other possible road users, you already have to deal, if you're in an urban environment, you already have to deal with pedestrians. You already have to deal with bicyclists. The scooters are out there. That's sort of already out there. There's certainly more things to keep track of. In a sense, that's just a computing power thing. You need more compute to take care of more things. The part that I think would be the most challenging is when you're driving down a street with a lot of chaos, in order to not hit things, it's not enough to say, well, I'm not going to hit what I see. You have to say, I'm not going to hit what's going to be there when I get there. Since I have a Pittsburgh theme, there's the saying, you don't skate to where the puck is, you skate to where the puck is going to be. And if you have objects that can change their motion very quickly, for those who remember their physics, second, third order derivatives, right, of motion, it isn't where you are. It's if you're going to change behavior dramatically and be someplace completely unexpected. So the way to look at it is, you see a pedestrian, it isn't where the pedestrian is. Then you see a pedestrian and you say, well, they're walking at this speed. I'm going to linearly interpolate where they're going to be. No, that isn't it. Every single object has a probability cloud around it. And you have to play the odds to make sure you don't intersect the probability clouds too aggressively. And the more different kinds of mobility there are, and the more different people there are using different kinds of mobility, every kind of mobility is going to have a different shape of probability cloud, and you have to sort of sort that out. So for sure, the number of participants matters from a compute power point of view. But from a design point of view, it's how many different shapes of probability clouds do you have to deal with, and how do you sort all that out? And if there's a novel source of mobility that you haven't seen before, how do you guess a good probability cloud for that until you have the experience? So that's sort of the way I look at it.
Yeah, let me build on that by picking up on. I'll get to all the questions in the chat, but I'll pick up on Sridhar's question, where he's asking about essentially what I interpret as a distribution shift question. So, how do you see autonomous vehicles in an Indian transportation context? So
well, we were sort of going there. I mean, and some places in China are also pretty challenging, right? Yeah, I mean, it's tough. If it's crowded, actually, if it's crowded and slow, it's easier because a lot of the challenge is, can you stop quickly enough if you guess wrong? And if you're moving slowly, that's a lot easier job than if you're moving quickly. So, complete chaos is different in that respect. But then you get to the point where, are you actually using the vehicle to nudge people out of the way? And that's a whole different dynamic.
Okay.
Whereas in the US, you generally consider contact with a vehicle to be a no-no. And I can imagine situations in which, yeah, of course, people are pressed up against the vehicle. Now what's your plan? So these things are going to have to learn the local driving style. There's no question about it.
You'd have to learn the horn protocol, right?
Yeah, the horn, that's right. Horn is as an actuator, that whole thing. Yep.
So Trenton has a question. He apologizes that if it's a bit of a cliche, but how many decades do you think until we would be ready to sleep/read in a self-driving car?
Well, I've known of people doing that for several years. But I'm assuming you mean safely, or whether I would want to do that and have a higher than I would and have a really good chance of waking up alive. I mean, that's where this ends up. It's not a matter of when, it's a matter of where. So most people on this call have been in a fully automated vehicle that it was safe to sleep in. If you've ever been to an airport and taken the automated train, a lot of those trains are built in Pittsburgh. The one in Atlanta is, the one in San Francisco is. I used to work with these guys, okay? And I'll ride the trains, so that tells you they're pretty good. Those are actually those types of trains are not on rails. They're on rubber tires on concrete treadways, and they qualify as a level 4 autonomous vehicle, and they're extremely safe. But they have an incredibly protected environment. They have the doors. So everything's sealed in. There's nothing they can really hit. So life is easy, right? So if you look at the progression of deploying fully automated systems, it's much more about the operating environment, how controlled the operating environment can be, and how non-chaotic it is. So you can go to sleep in something that's in a very benign environment. Once the environment gets chaotic, then it gets harder to do. And this is going to take decades for this stuff to roll out. And maybe there'll be in a particular city that has it all together, and that's great. But if you want to jump in a car and go across country, including through urban centers, it's going to be a long time, and that ends up being as much economics as anything else. But so when we solve the AGI, the artificial general intelligence problem, then it'll be easy. But until we do that, I'm not holding my breath, I guess.
Okay, so here's a question from Oleg. And hopefully I get this right. And if I don't, he can follow up with me. So as human beings, we use a kind of reinforcement learning to deal with dangerous situations. Our blood pressure goes up, we get feedback signals, and we react. So we're getting rewards and sort of positive and negative rewards. What's the role for this kind of reinforcement learning in simulations and other forms of testings? To develop better AV software?
Well, I don't have a religious preference for which type of AI you use, but what I do really care about is when you get on public roads, you have to ensure safety. And so one of the things that's important is if you want to use reinforcement learning and learn from experience, from a safety point of view, if every system has a different behavior, there's an advantage to diversity, that the entire fleet won't fail the same way on the same day because leap second or something, right? Hopefully that you don't have that problem. But guaranteeing safety is really hard because there's no way to validate these things in an engineering environment if everyone's different. There are some things for length. There's a whole rabbit hole I could have gone down that I didn't for length, having to do with safety envelopes. That one of the classic architectural patterns, I call it doer checker, but it's been around for a long time. You'd put a safety envelope or safety cage around the behavior and say, hey, the AI can do whatever the heck it wants as long as it doesn't cross this boundary. And then there's a non-machine learning based system that enforces the boundary, puts a cage around it, right? And then you can reinforcement learn all you want inside as long as it gets chopped off at the knees if it does the bad thing. That pattern works pretty well for path planning. Don't hit stuff. You put an occupancy grid down. You say, don't enter a square that has something in it. Okay, great. But you have to predict where the occupancy grid's going to be when you get there. That's part one. But part two is, what if the perception system doesn't see the thing? And that's the hardest part. So you can use the safety envelope pattern for most things, but for perception, we don't know how to do it that well. You can approximate it, but it's, ultimately because you have to do prediction, that's the hard part in safety is figuring out a safety envelope for perception.
So Avram has a question, a comment that kind of I think connects to something that you've pointed out, previously in this discussion. He asks, does reducing the problem scale reduce the complexity? What if you only deal with travel at a certain time of day or in a specific area or between particular cities? Does this scope the problem such that it's more manageable now?
Maybe. I mean, I started out talking about the more benign environment. The limit to this is, and I'll be giving a talk at Seams next week, a keynote at Seams that goes into this in a lot more detail. There's a plug. And for those of you who didn't register at Seams, it'll be on YouTube after that. But the heavy tail is the issue that you have a large number of things with low probability, but in aggregate, the area under the curve is too big to be safe if you ignore them. And so you can say, well, I'm only going to drive on this one stretch of road. And in principle, we'd think that would make your life easier. But the question isn't, is it just one piece of road only during daylight? It's what's going to happen on that road. And so, the truckers right now, the automated truckers are like, well, we're on the highway in the middle of Texas and what can go wrong? And, I've seen the videos of the tumbleweed Armageddons and the tornadoes and all this stuff can happen, weird vehicles on the road. All this stuff can happen and probably will within the vehicle lifetime. So you don't have to drive despite it, but you have to know something weird went down and deal with it safely. So limiting the operational design domain, ODD, is the only way this stuff is going to work, which grasps the essence of how do you limit the complexity. But you have to realize it isn't just the geography, it's all the things that can happen. So yes, I only drive not in urban downtowns on this one stretch of highway, and I've gone an entire year, collected data, and I'm really good that every time I saw something weird, my system knew it was out of its depth and did a safety shutdown. Okay, now that gets to be a story I can believe. But just saying, oh, it's one stretch of road, we tested for a week, we didn't see anything weird, it'll be fine, that's not going to get you there.
Yeah. Great. Okay, so Charles has a question. So what are the biggest gaps you see between academia's autonomous vehicle testing research and what's being done in industry with respect to meeting the safety requirements of different autonomy levels?
The academics don't have the resources. They're mostly just training folks to work for industry. Way back when this started, I was working at National Robotics Engineering Center. I sort of told that story on the slide. And then one day I went into work and the parking lot was empty. And I started asking, how come our parking lot is empty? It's like, oh yeah, Uber just hired everyone. And that's how Uber ATG started. So they're basically hiring all the folks out of academia. There are some really good researchers in universities, to be sure, but there's tremendous financial and other pressure to get hired away to industry. And frankly, the industry has the resources the academics don't have. So for sure, there's really good work going on in the academics area. There's no doubt there's really good long-reaching work. But the universities don't have the resources to stand up 100 test vehicles and drive them every day around a city and set up the data farms. That's just not where the universities can compete right now.
So here's another question from Trenton. I'm gonna paraphrase a little differently. So he asks, are there any regulatory agencies that are setting up local regulation appropriately? I'll add to it. Are there any regulatory agencies that are kind of doing it the right way in your view?
Hi, Trenton. I used to work with Trenton, so thanks for the question. The issue with local regulation is very complicated. I've spent some time this year participating in different states doing their regulations, and the AV industry is doing a barnstorming campaign from state to state, trying to get past the weakest possible regulation. Basically, come to our state, spend money, do whatever you want, it'll be fine. And in most places are not doing a very good job pushing back. Some are pushing back, but it's pretty bad. They're doing things like saying, well, if there's a crash, it's the computer's fault. And the implication is unclear, but it seems like if there's negligent driving, you put the computer in the jail cell and somehow that's going to make it better. I'm not making this up. It's terrible. There's a couple rays of hope. New York City actually requires the industry to follow its own testing standard. And Massachusetts strongly suggests it, and that's about it. No one else even requires that they follow J3018, which is the industry's testing standard. So mostly the local regulations are kind of a mess. There are some states that are working hard on it, but it's very tough, and the industry has lots of resources to lobby here. So it's a constant battle right now.
So Carl asks a question about your comment that we're 98% of the way towards the solution, but the last 2% is really hard, and there are these kind of countervailing pressures. Industry wants to push and get this technology out there for their own reasons, and maybe society more broadly wants to put the brakes on. So how do you see this balancing, and how do you see researchers being able to sort of get in there and help facilitate sort of a safe closure of that last 2%?
It's tough for sure. I know the ethics was someone else's keynote, and I don't want to go there too much. But in my mind, the biggest ethical concern right now is the governance question, which is who gets to decide this stuff is safe enough to put on public roads and how they decide it. And right now, the situation is the companies do it with complete opacity. They just do whatever they want. And so pushing back on that is important. But that I spend a lot more. I never thought I would spend time on the phone talking to congressmen and stuff, but that's my life now, in part. A lot of it's just political. It's not technical. From a technical point of view, the issue is the core research issue is how do you know that a machine learning based system doesn't know what's going on? It's how does it do distributional shifts? And the issue going deeper ends up being that people say, well, we know that this is close to something else we've seen. I'll use perception. There's this object and it's close to this thing, and so we're going to say it's the same object. But what we found, I've done a fair amount of work in this, trying to tease apart what's really going on, what the failures are. And a lot of the failures we see are that there are two objects that are close in every dimension except one dimension. And that dimension turns out to matter, but wasn't represented in the training data well enough for it to care about. So, for example, people in yellow clothing don't get seen because yellow turns out not to be a person, and there wasn't enough training data for people to realize that yellow is a thing, right? And so people say, oh yeah, this aggregates all the cases that are close to each other. Well, the failures I often see are their notion of close ignores a dimension that matters and causes failure. So working on the heavy tail in weird stuff happens, but not necessarily getting it right. Simply saying, hey, this is something we've not trained on, and we've not trained on a dimension that no one ever thought to worry about before. If you can solve that problem, then we have something, because it's not about working all the time. It's about knowing when it's time to call it quits. People are amazingly good at that. People are good at, what the heck is that? I'm going to slow down until I figure out what's going on. And these systems typically are pretty bad at that if it's a dimension that someone hasn't already thought of.
So maybe I'll jump in here, because you brought up this question of governance and who makes the decisions about, I'll say, what's important and what ought to deserve our attention. And just for everyone's sake, I already tipped my hand to Phil that I was going to ask him a question that kind of tried to bridge the three keynotes. And so on the first keynote, we heard about the spread of disinformation and the challenges there, both within science, but broadly in society. And then yesterday, Professor Simon was talking about values in the design of systems. And that generated a little bit of discussion on chat that's kind of stuck in my head. And it was kind of brought up by a question that Bashar and Sebe asked. And I'll frame it this way as a kind of a hypothetical. So let's imagine that we view more software as being mission critical, not just the traditional safety critical, mission critical.
Oh, everything's getting mission critical. No argument for me there. Yep.
Let's think of a social media platform as being a mission critical piece of software. And let's imagine a couple of critical properties. One, and I'm just putting them out there, one is that it should support free speech, and the other is that it should prevent the amplification of disinformation. Okay, if that's the if that's what we believe and that's what we want to happen, how would sort of the safety engineering mindset be brought to bear on that? And what kinds of conversations or domain experts would we have to engage with in order to, move forward in applying all of the, rich body of sort of process and technique from safety engineering to, more broadly to software?
Well, being equipped with a hammer, I'll use my hammer to beat on the thing that isn't a nail. That's fine. The safety case. So there's a slide that said safety cases. You have a claim and you support the claim. It's not really a safety case. It's an assurance argument, and you're assuring whatever property you care about. It's just that when I talk about safety, it's easier for people to see what I'm getting on about, right? But it's an assurance. We want to assure anonymity. Okay, well, how are you going to do that? And what are the threats to anonymity and all these other, what about the de-identification, the re-identification attacks and all this other stuff? So it's a structured way to make an argument that you think that you actually have the property you think you have. So I would sort of go at it that way. What are the hazards? What are the threats? Security and safety look pretty much the same from a certain point of view. Maybe the security guys are all cringing, but a lot of the stuff I do for safety, you have to have security too. Of course you do. And they all look like threats against the validity of the claim that your system is good, but they take different malicious versus non-malicious attacks, of course, are different. But that kind of framework can help. Well, let me insert another, since I have the Keynote soapbox, I'm going to insert another soapbox item, which is part of the problem we have is that we think that coding camp makes you a software engineer. As a society, that's a big problem. And as long as we keep fostering that, we're going to see horrifically bad systems that end up being life critical or at least safe mission critical for our lives. So that's, people call it code quality, bad code, but it isn't really. It's lack of an engineering mindset for building these systems, for intentionally designing them. And the assurance case is just a way to structure an antidote for that. But I mean, software engineer after 6 weeks of boot camp, you got to be kidding me.
Yeah, my takeaway from this week of keynotes is that every software system is mission critical.
I'm not going to disagree. And just in the autonomous vehicle point of view, okay, so you're hosting your HD maps on AWS. Guess what? And you need your maps in real time or there's a crash. Guess what? All this stuff that no one ever thought was life critical is being levered into being life critical because someone's using it in a way. And the no life critical click-through disclaimer isn't going to stop them from doing that.
All right, so back to the questions from the chat. Thanks for entertaining mine. So currently, the 6 levels of autonomy are vaguely defined with terms like most driving tasks, particular situations.
Oh, the SA levels are terrible. They're horrific.
How do you think we should regulate, say, or should we establish boundaries between levels of autonomy? And if so, how should they be defined?
Well, my Safe Autonomy blog has multiple proposals on this. I have a recorded half-hour talk on it for those who can stand listening to me more. But let me sketch out the way I look at it. That the levels of autonomy from SAE are arguably useful for engineers, but they're about which boxes you put in and how the boxes work. And that's not particularly useful for regulators. It's opaque, very difficult to understand. Almost anyone who writes an article gets it wrong one way or another because they're very, very complicated. I'm on the voting committee for that thing. I'm not claiming responsibility. I joined after, but I've spent hours and hours and hours trying to understand, and almost no one ever gets it right when they talk about it. And there's a history why that is, but it's just the wrong tool for the job. And so communicating it doesn't do a great job at communicating, but for laws, it's actually actively hostile to laws because there's loopholes like the level 2 loophole. If you just say you don't ever plan to make it fully self-driving, then you don't need any permit because you can call it level 2. It's ridiculous. I look at it this way. There's different levels. One is either you can go to sleep in the back or you can't. It's binary. The latest system I've come up with, because I've taken several cuts, is there's systems where you're driving and the car helps you. There's systems where you're watching the car drive and it's your fault if it crashes. Whether deploying those systems is a good idea is highly controversial, but they exist, so we have to have a bin for them. So there's, you're in charge, you're watching. There's one where you're sleeping in the back, or it's no crew. And the fourth one is there has to be a thing for testing, for road testing, where you have to have a trained professional driver. And most of the dysfunction I see is people trying to confuse those bins to get advantageous regulatory treatment for being in a bin they don't really belong in. But it's just either you're driving or it's driving. It's driving and you're holding the bag if something goes wrong. Or legitimately, there's nobody, whether it's just a passenger, that's it. And then there's testing. Those are the 4 bins. And if you regulate according to that, a lot of the dysfunction goes away.
Great. So actually building on that, so Jingyu has a question I'll characterize as who watches the watchers question. And, the regulation is governed by this safety certification process run by people, auditors.
No, there is no safety certification process in the U.S.
Okay.
But keep going.
Run by people.
Keep going.
What sort of competencies should an auditor have to be able to certify AV properly, and how would you certify the auditors?
Okay, so let me unpack why I said what I said. In the US, anyone can put a car on the road if they meet the crash safety and other basic federal motor vehicle safety standards, but they have nothing to do with software. Do your brakes work? Are your headlights bright enough? Do the airbags deploy? Software safety does not enter into it at all. Anyone can put a vehicle on the road, have fun. If there are a bunch of crashes and a bunch of injuries and fatalities, NHTSA will get on your back about fixing it. And maybe the lawyers will come after you, but it's very hard for them to litigate cases involving software bugs. Very, very difficult unless it's an easy bug to repeat. So it's really kind of a mess. Now in Europe, they have type approval, but the type approval is back to, are your headlights bright? Did we drive it for a couple thousand kilometers and nothing bad happened? There's no software safety requirements anyway. So that's why I went down that road. If you use ANSI UL 4600, which is the standard I talked about, that standard requires the team who designed the vehicle to create a safety case saying, this is why it's safe. Here's our claims. Here's our argument. Here's our evidence. It has a requirement for independent assessors to come in and look at the safety case and ask the hard questions about, well, you claim this, but your argument doesn't make sense or your evidence doesn't support the argument. And those independent assessors have to be, finally, I'm getting to the answer to the question, have to be accredited somehow. And in the US and actually internationally, there's actually a process for that. ANSI, American National Standards Institute, has a way they accredit the accreditors. So in every industry except automotive, they actually do follow their safety standards. And there are external assessors who check that they follow the safety standards. TÜV is one, Exida, some others. Underwriter, UL.com in the US does some of the standards. UL.org issues the standards that UL.com assesses. And they're all accredited under this ANSI thing of who checks the checkers. So there's a robust ecosystem that already does the independent external assessment. It's just that the automotive industry is not required to use it, and some do, but there's no requirement. A lot don't.
Yeah, I've always been flummoxed as to why it is that industry gets that take. I understand the history. I know there was a lot of power players.
No one has a gun to their head. Look up the word regulatory capture. Just look it up.
So here's a question from Ted. The number of miles required for safety, in quotes, argument appears to get weaker when we see hundreds of thousands of Teslas being deployed every, unit of time in the US. And it feels like that's just a way of parallelizing data collection. Is there another way to kind of frame the question in terms of how many deployed cars would be required collecting the data in order to kind of facilitate, sufficient evidence, let's say?
Well, it isn't the number of cars all collecting the same data on the same road, which I know isn't what you said, but that's the pitfall, right? It's that you have to have good coverage of the edge cases of the rare events. But the issue with putting out a lot of cars on the road is the safety of what's going on while you're collecting the data. So if you have completely manually driven vehicles and it's completely passive data collection, which some companies do on trucks, there's huge huge corpuses of data on trucks because they have monitoring systems, even though the driver is doing all the driving. So there's a lot of data you can get from that. But as soon as you let the autonomy system have some control while you're driving, now you're doing on-road testing. And the question you have to ask is how much risk are you presenting to other road users while you're doing the testing? So the amount of data is for sure in the billions of miles, for sure. But that's not enough. There has to be diverse data. It can't just be on the same roads. And you have to know where the weird stuff is, which is the hard question. How do you know the weird stuff if your system doesn't know what the weird stuff is? You know, this is where it gets tricky. And you can say, well, we need the automation to make mistakes to learn. It's like, if you're going to say that, what's your plan to keep all the pedestrians and vulnerable road users safe while you're doing it? And taking a retail customer and say, congratulations, now you're a safety driver. By the way, you're the one who goes to jail if there's a mishap is not my preferred approach.
Yeah. Thanks. Sangeeth says, thanks for the great talk. I think I'll get this question right. So how do you think about the fact that the perception and decision systems are trained or developed most probably using software that itself is not safety certified, and then they are in turn used in safety critical contexts?
There's a reason. There's a tool qualification section in UL 4600, and that's the reason. For anyone, so I know I wrote most of the standard. It is an issued standard. Lots of people had great input, and it would be nowhere near as good without it. But I did write a lot of it. A lot of it's in there because what I wanted, and tool qualifications in there for exactly this reason. So you're going to use some software developed by a bunch of grad students to get their thesis, who are smart, but they're not trained in critical software. And the tools are out there and they work pretty well. And now you're going to trust your life to it? Really? I know I wouldn't trust my life to my PhD thesis code. Not a chance, right? and so tool qualification is a big question. And in the machine learning area, that question, falls flat. You don't get a lot of answers. Now, if you have a separate safety system that guarantees safety, even if the tool missed something, or your data wrangling, you systematically are excluding as outliers things that actually matter because they're edge cases. Or I've seen data, it's common to have data labeling errors of like 5% incorrectly labeled, which may come out in the wash for things where there's a lot of them. But if there's only a few samples of something and they're incorrectly labeled, you won't even know they're there. So it's not even the tool qualification, it's all that stuff. And if you need a couple nines because you're doing Netflix recommendations, which I actually believe has social value, thank you for doing that. But if it's someone's life on the line, I go to these workshops where there's some AI type people and there's some safety people, and the machine learning folks will say, I know I'm using AI very loosely, please forgive me. The machine learning folks will say, hey, we have this cool thing and we're at 99% on whatever metric they're using. I know about ROC curves and all that. I'm just keeping it simple. Okay, they're at 99%. And I'll say that is genuinely very, very cool. And for some applications, that's amazing, great progress. 7 more nines to go.
Yeah. Yeah, and the question I always wonder is, okay, you retrain your model 10 times, and it's 99% test accurate. Is it the same 1% every time?
In principle, no. Yeah. But in practice, the issue is, so let me go there for a second. The issue that I've seen that is really problematic is that 1% has systematic patterns to it. If you had 99% accuracy and you could guarantee the 1% was completely random, and you had 2 of them that were 99% and it was completely random and there was no common cause failure, you could start playing the reliability math, right? But what we're seeing, what I see very often is the 1% is because of systematic biases in the data, or gaps in the data, or aspects of the data that no one realized mattered. And so you can say, hey, or just rare events. It's like, oh yeah, we're 4 nines, 99.99% on pedestrians, but we see 0 people who ride wheelchairs. That's not going to work.
Right. So N-version programming doesn't work here either.
Well, N-version is that's the community that I come from. N-version is highly controversial to begin with. And for anything with software, and you can say people want to do N-version for machine learning, but the issue has always been how do you measure diversity, and no one's ever had a good answer for that,
Yeah.
other than brute force testing out beyond the limit of the acceptable failure rate of the diverse models.
We have one last question here from Tim. I want to hear the answer to this one. How do large car companies react/interact with your work?
Do large car companies?
What do large car companies think of your work, and do they interact with you, in particular ways that you're willing to share while it's recorded?
It depends on the car company. Some car companies are not fans of my work on unintended acceleration. It doesn't take much imagination to figure out who some of those might be. It is what it is. Other car companies so I talk to car companies all the time. My take is that the rank and file engineers want to do the right thing and want to do the safety. The business people have a more complex life because they have investors and shareholders to keep happy by meeting their milestones. So I actually spend a fair amount of my life now helping car companies do the right thing very quietly. And that's okay, because ultimately it's about doing the right thing. So there are some I can say publicly that, a lot of things are a mess, but I try always, and if I missed it, forgive me, to say some companies are struggling. Some companies are quietly doing the right thing. I can't tell you which ones they are. So there's some hope here, but it's a really hard problem. And you have a financial environment where you're chasing trillion-dollar markets and there's tens of billion dollars in play. And if somebody says, no, you can't do the demo because you don't have safety lined up, and because of that, your company's going to collapse, you're putting even the most well-intentioned CEO in a really tough position. And so that's just the way it is.
Well, we're going to take all of your time, if you don't mind, because we have about 4.5 more minutes, and a couple more questions came in.
Okay.
Go for it. So I'll paraphrase this one from Trey a little bit. UL 4600 is great. Let's imagine that industry follows that, wants to follow that. Where are the gaps in the research? Is it related to methodologies, testing techniques, tools, better understanding of underlying components, whether it's software components or machine learning components? Where are the biggest gaps?
The big gap. So 4600 doesn't tell you how to fix the safety problem for machine learning. It tells you how to argue in a reasonable way that you fixed it. And I'm keenly aware that those are not the same things, which is the point of your question, right? The big thing is the heavy tail of what do you do about lots of things you've never seen during testing, you've never seen during training, but the aggregate risk accumulated across all of them is too big to just sit down and deal with. 4600 has a feedback, and this is my Seams talk next week, has a feedback mechanism built into it to try and bootstrap yourself that as long as you have a high safe failure rate, any way of detecting that something not quite right happened, even though there was no crash, maybe you can get ahead of it before the crash happens. So looking at going from the traditionally in safety, you're safe for the life of the product the day you release, in theory, and like that's just not going to happen. So getting to tight field feedback loops, but still being responsible about only deploying things that are pretty good at safe and keeping ahead of the bootstrap curve is one. Another one is just dealing with how do you get 9 nines out of machine learning? How do you even do that? Because ultimately, there's lots of things you can do, but ultimately, it's 100 million miles between fatalities for people, and that includes all the drunk drivers. So how do you get machine learning that isn't going to kill someone more often than every 200 million miles? That's a lot of nines, right?
Yeah.
So how to do that, and maybe the answer probably isn't all machine learning. It's probably some hybrid, but that's fine, right? And there's a lot of arguments. So you can do a lot of good, but ultimately you have to have the combination that gets you there. So that's one. And another one is just taking a more principled approach to go back to your earlier question about lots of software is mission critical. There's a time and place for good enough software. Mary Shaw always likes to say, there's good enough everyday software, and that's great. But lots of the software is becoming more critical than anyone really appreciates. and trying to get more of an engineering discipline into doing the right thing for high criticality software really matters for the whole profession.
One last question. Just so you know, Phil, when that timer goes off, we're off the air. But
Ding. Okay.
we'll try to get to this question quickly. So it's from Timothy. I think it's a distribution question. So at one point you mentioned paved roads, but in many countries there aren't paved roads. There aren't very many. It's dirt roads, and in other places there's a lot of snow-covered roads. So how do you deal with this?
Well, I just used paved roads because it was an easy query from Wolfram Alpha and gave an impressive number. Yes, unpaved roads matter. I've lived on a gravel road. I get it. The question is, where do you want these cars to operate, these vehicles to operate, and what are they going to do? And over time, the operational design domain will expand to more and more roads. If the first day it's just trucks going from depot to depot on heavily mapped paved interstate highways that get daily pothole scrubs, okay, fine. If you can make that work, fine. I mean, it's all about finding an economically attractive deployment that has very, very constrained, relatively benign operating conditions. Maybe you close down the road for 10 minutes and the convoy of trucks goes by with no way through. And if that works, good for you. But it's all going to be about trying to find the economic sweet spot between simplicity and being able to make the service pay for itself.
All right, with that, let's thank Phil.
Thanks, everyone.
That was great.